All right, so what we have here is all about rational functions and their zeros. We're also going to learn about their asymptotes. What do we know here? Well, let's find the domain. To find the domain, what we want to do is we want to take a look at the bottom, and we want to set it equal to 0. So if I was to do that, I would have 2x squared plus 4 equals 0. And I just solved this. Well, the first thing I could do is divide everything by 2. That'd be, like you just imagine dividing both sides by 2. You get x squared plus 2 equals 0. Then you subtract 2 from both sides. You get x squared equals negative 2. Well, if you think about it, there is nothing that when you square it gives you a negative number. So that means this domain is all real numbers. Usually we just put a capital R for real. You could also write it like this. Hey, everything from negative infinity to positive infinity, just all real numbers. All right, what about the zeros? Well, the zeros are anytime the top equals 0. And you can think about that because, like, if I did, if I had, like, 0 divided by 1, obviously that's 0. If I had 0 divided by 2, obviously that's 0. If I had 0 divided by 137, that's still 0. So it doesn't matter really what the bottom is. It's just that the top is 0. So to do that, we're going to factor this top. So I need something that multiplies with the negative 8 and adds up to 2. I think I could do that with a 4 and a 2. How about a 4 and a negative 2? That should work. So I get x plus 4 times x minus 2. And if that was to equal 0, I would get zeros at, I'll write them down here, x equals negative 4 and positive 2. Boom. And sure enough, that's what we see here, right? There's my zeros. We don't, the domain does appear to go from negative infinity to positive infinity. Yeah, we get this little like weird curvy thing to it, but there's no asymptote or anything like that. So we're good. All right, let's look at another example. What do we get? How do we get a whole? Okay. Oh, and down here is what I just said, basically. If n of x is 0, then the whole thing is 0. Well, let's talk about the domain. Domain, again, we want to focus on the bottom. We want to say, when does the denominator equal 0? Because that's when this thing would break. Because we can't have things divided by 0. So the first thing we do is just say, hey, x minus 4 equals 0. And that would mean that x equals 4. But really what we should say is x minus 4 can't equal 0. And therefore, x can't equal 4. And so we could write that as part of our domain. So maybe the domain could look something like this. I could say, hey, it goes from negative infinity to 4. And then from 4 to positive infinity. That's one way of writing it. You could also just write this. You could say all real except that x cannot equal 4. That's another way to write it. So lots of different ways you could write this. All right. Now, let's do this with this thing. I bet we could factor the top. So if I found something that multiplies up to 12, adds up to negative 1, I think we could do a 4 and a 3. How about a negative 4 and a 3? That means this thing would look like, kind of need a little bit more space. I'm going to zoom in. I'm going to do it in blue so we can tell the difference here. It would look like x minus 4, parentheses, x plus 3, parentheses, over x minus 4. And now we got this weird situation where we have factors that actually cancel. However, the problem here is, yes, they cancel. And yes, g of x essentially looks just like the line x plus 3, except for the fact that when you cancel, when factors cancel, you get a whole. So we have to still keep in mind this fact that x cannot equal 4. So that's like a simplified version of our function. And what are the zeros? The zeros are just when this top thing equals 0, which is at negative 3, right? So we could say x plus 3 equals 0. Solve that, we'd get x equals negative 3 as one of my zeros. All right, so what does this look like graphically? Well, graphically, it looks really simple. It just looks like the line with a slope of 1 and a y-intercept of 3. So it looks something like this. Except for when you get to 4, we're going to put a hole. Because this thing essentially looks like this line, except for it started off as a rational function over here. And so we have to account for the fact that It doesn't exist right here when x is 4. Other than that, it looks just like a line. So that's worth just making a big flashy note of, right? Like this is something you really want to make sure you know. When factors cancel, that's when you get a hole, okay? All right, let's move on. Let's talk about vertical asymptotes. Ooh, let's talk about this. Fun stuff. This is when things do not cancel on the bottom. Let's go ahead and factor both the top and the bottom. If I factor the top, I'd have 4x plus 2. And on the bottom, need something that multiplies up to -10 and adds up to 3. How about a 5 and a 2? And how about 5 minus 2? Yeah. So that'd be x plus 5, x minus 2. That does not cancel. Looks like it might, but it doesn't. It's not the same. X plus 2, not the same thing as x minus 2. So nothing cancels. So my domain, where I have domain problems, is here, where these things would equal, or in this bottom would equal 0, right? So I could set the bottom equal to 0. And remember, it can't, really I could say it can't equal 0. And x minus 2 can't equal 0. And then I could solve each of these. So x cannot equal -5, and x cannot equal +2. And so that's how I figure out my domain. And so now I know that this thing is going to go from -infinity to -5, from -5 to 2, and then from 2 to +infinity. And there's my domain. Okay, what about holes? Well, we don't have any holes because nothing canceled, right? We didn't have anything that canceled, so there's none, no holes. Zeros are easy. We just take our top and we set it equal to 0, right? So for the zeros, I'm going to say that 4x plus 2 equals 0. And I really, because this is just a coefficient, imagine if I divided both sides by 4, then I would just have this. I would just have x plus 2 equals 0, because 0 divided by 4 is still 0. So we really only care about this linear factor here. And if I go to solve that, obviously I subtract 2 from both sides. I get that x equals -2. And so that's my only 0, that x equals -2. And sure enough, we see that on the graph over here. Now, what about vertical asymptotes? Vertical asymptotes are the zeros here that we found. Or I should say the restrictions to the domain that we found. So the vertical asymptotes are going to be at x equals -5 and x equals 2. And you can kind of see that visually here if I like kind of sketch in this graph. Here's where x is -5, and let me just kind of zoom in over here. And here's where x is +2. And sure enough, that comes up in our graph as vertical asymptotes. And there we go. That's how we can find a vertical asymptote. So if it doesn't cancel, you get a vertical asymptote. If it does cancel, then that's when you get a hole. Let's go to the next page. All right, so let's take a look at this guy. Again, first thing I want to do really is just factor this thing so I know more what I'm looking at. So over here, the top is a difference of squares, so I'm going to write that as x plus 3 times x minus 3. And on the bottom, I need something that multiplies up to -3 and adds up to -2. I think I could do that with a 3 and a 1, but a -3 and a 1, right? So I'm going to write x minus 3 and x plus 1. And sure enough, I do get a cancellation here, which tells me I'm going to have a hole. So I'm going to have a hole at that 0, which would be x equals 3. When do I have zeros? I have a 0 right here for this 0. When that top would equal 0, that'd be -3. Vertical asymptote, that's when it doesn't cancel. And so that'd be x equals -1. And so we could say our domain is -infinity to -1, 1 to 3, and then 3 to infinity. And then remember, this is going to be the hole, and this is going to be the asymptote. So what about a vertical asymptote? Vertical asymptote, sorry, we already did vertical asymptote. What about a horizontal asymptote? This is super easy. If the degrees are the same, which in this case they are, right? They're the same here, and really they're the same here, because these are both x minus 1. Then all you do is you take the leading coefficients and you put them over each other. So 1 over 1 equals 1. So that means we have a horizontal asymptote at y equals 1. That's all you got to do there. Pretty straightforward. There's other rules if the degrees don't match. Like if the degree is higher on top, then there's not a vertical asymptote. It's just going to keep going up and up and up forever. If the degree on the bottom is lower, so if this was like x to the 1 and this was x squared, we'd end up with a horizontal asymptote at y equals 0. All right, what else are they asking here? Oh, y-intercept. Y-intercept. So this is when this is plugging in a 0. Okay, so this is at x equals 0. So what we're going to do is we're going to take our equation. It doesn't matter which one, because we should end up with the same value either way. But I find it actually pretty easy to plug into the original, because if I plug a 0 in here, I get a 0. If I plug a 0 in here, I get a 0, and I plug a 0 in here, I get a 0. Let me just kind of show you what I mean by that. Like if I was to come down here and I was to say, okay, h of 0, what is that? Well, it would be 0 squared minus 9 over 0 squared minus 2 times 0 minus 3. Well, that's just a 0, that's a 0, that's a 0. So really just have negative 9 over negative 3, which is positive 3. So our y-intercept is at x equals 0, and it's y equals 3. So we could write it like this. There's our x-intercept. If I would have done the same thing for this version, for the factored and canceled version, if I plug a 0 in here, I get 0 plus 3 over 0 plus 1. 3 over 1 is still positive 3. So there we go. No matter what, we get the same y-intercept. And that's it for that problem. We got all the pieces. Let's go on to another one here. Now they're giving me this funky graph, and they're not giving me the function, but that's okay. What's the domain? Well, the domain, from what we can tell, obviously there could be more information here that didn't graph, but this little arrow implies that it keeps going in that direction forever. So the domain appears to be from negative infinity to some horizontal asymptote, which I think we can kind of, sorry, I keep saying horizontal, that's incorrect. Vertical, I mean. To some vertical asymptote here, which I think we could surmise to be at x equals negative 4. That's what it looks like to me. So we could say this thing goes from negative infinity to negative 4, then it hits an asymptote, and then in union with negative 4 to, ooh, we have a hole here, so what is that, 2, 4, 6, 8, so that's 7. So negative 4 to 7, and then from 7, sorry, I moved it down here because I was running out of room, from 7 to infinity, right? So we have from negative infinity to negative 4, negative 4 to 7, then we have a hole, and then infinity. And what, again, what's going on here? So this is the asymptote, and this is the hole. All right, let's break down all the pieces now. We know where the hole is. We just said it. We can tell that there's a hole at x equals 7. What are the zeros? We could tell by looking at the graph that we have zeros here and here. So it appears that we have zeros at, I like to do my little add symbol, at x equals negative 2 and 2. Vertical asymptote, yeah, we established that that's at x equals negative 4. Horizontal asymptote. So it does, there is some, looks like maybe there's some asymptote here, but it's not horizontal. It looks like it could be some type of line, but that's not horizontal. So this one we would just say none. And the y-intercept, well, for this part, we're going to have to just guess. Y'all did in green. I mean, obviously, it's crossing right there. It looks like it's not quite to negative 1/2, so I'm just going to say I'm approximating it to about negative 1/3. Really don't know, though. That's just an estimation. All right, I also want to get in the habit of being able to do a sine table. This is going to be really useful for us in the long run. I have the whole domain down here. Okay, and you may be going, well, what about these? Why these are not where the domain breaks? You're right, they're not, but those are our zeros. So we're going to keep those in our chart. So I'm actually going to put a 0 there and a 0 here. But what else is going on? Well, from negative infinity to negative 4, we know the value is negative. At negative 4, we have an asymptote. So I can do one of these things, and I might even want to say, like, that's an asymptote right there. From negative 4 to negative 2, it's positive. Then from negative 2 to 2, it goes negative for just a little bit, and then it goes positive again. Then we have does not exist because we have a hole, and then it's positive. And there we were able to fill out all the information about this function. Isn't that beautiful? Got all kinds of beautiful information. And really, those are all the different kinds of examples you're going to see. Yeah, so you're looking for just certain pieces of information to help give you different things. If we kind of go back over it, right? If they cancel, you get a hole. If they don't cancel, you get a vertical asymptote. Horizontal asymptotes, we talked about that up here. It's if the degrees match, it's just leading coefficient over leading coefficient. Y-intercept, there's nothing new about that. And then your domain is just listing all the x values where this thing exists. And usually you're going to start from negative infinity, go to positive infinity, but sometimes you won't. Like sometimes I could have, if I would have put a solid dot here, then I would have had a clear beginning, and I could have put a solid dot here and had a clear end. That's possible. Anyway, I hope that's good. I'll see you guys in the next video.